get started. So our first talk will be by Rong about connections between South and North American monsoon. It's a very interesting issue and not much explored. So please tell us what you found out. So, yes, with this, the camera will follow you. Then the microphone.
Okay, good. You can hear me. So, first of all, thank you very much for get up early and come to this summer school. And I really appreciate Alice and the committee for putting together such a nice program. And I think this topic was actually requested by Alice. I hope I'm not disappointing. And I wish I could give a overview like what Francina gave yesterday. But really, in this area, there are very little research. So unfortunately, a lot of work will be preliminary and will be focused on my result because I couldn't find a lot in the literature. So I would like to acknowledge the important contribution from my former research scientist and student, Hui Wang, Paula Ayres, Tong Ren, and Adam Baumann, and also inspiration from many well-known scientists sitting in this audience, as you will see. We know if we look at the literature, and there are many studies we can find to show that the North Atlantic Oscillation or tropical North Atlantic sea surface temperature anomalies, which is SSTA here, can influence the South American monsoon. And there are many studies. This is just a select few. But very few studies we can find in literature to address the potential influence of a South American monsoon on North Atlantic and the North American monsoon. So I hope this will be the focus of this presentation. With very limited evidence reported in literature, and they are the limited evidence we can find in literature does suggest the possibility that South American can influence both tropical and mid-latitude Atlantic oceans. So here is two examples. And one is Pavardi and Mesa, and they look at the long-term river flow over Colombia and also the Atlantic sea surface temperature anomalies. And what they find here is that the correlation between Columbia river flow anomalies and Atlantic sea surface temperature 3 months later is stronger than the correlation between Nino index and Atlantic sea surface temperature anomalies 3 months later. That's the bottom panel here. This is a correlation with Columbia River. And another example is a modeling study by Gurney and Weldes in 2000. So here they look at the Hartley model where they deforest the Amazon and that generate diabetic heating anomalies. And this is the circulation response over North Atlantic and Europe. So what their paper suggests is when you deforest the Amazon, and this is entirely deforested Amazon rainforest, and you will see this influence on North American, on North Atlantic Europe through the latitudinal propagation of the Rossby waves. But this is the modeling result. Actually, Peter Cox told me they didn't believe it. So the question is, can we find observational evidence to suggest this kind of a wave propagation in reality? So the overarching science questions motivated our research is how is North and South American monsoon climate connected? And could variation or changing of one American monsoon affect the other? And if so, what are the mechanisms behind such influence? So these are overarching goals, and by no means we know the answer for these questions. So the most obvious mechanism is the cross-equatorial propagation of the planetary wave or Rossby waves. And so this is reported in literature even back in later 60s by Charney, Dickinson, and Webster and Houghton. And so the cross-equatorial, and also let me mention my favorite author. So here's Alice and Pedro's work, and Tertial and Koskin's work. They're all address this latitudinal propagation of the Rossby waves. So the latitudinal propagation of Rossby wave require westerly wind in the upper troposphere. But if you look at the equator, it's dominated by easterlies most of the time and most of the place, except the two windows. This is a weak westerly over Eastern Pacific and a weak westerly over the American Atlantic sectors, and mainly during the boreal winter or austral summer, DJF, December to February. And so this is referred by Webster and Houghton as a westerly duct. And most of the cross-equatorial Rossby wave study has been focused on Pacific, this westerly duct. And related to that is the interhemispheric connection between Asian monsoon and Australia monsoon, as well as Asian monsoon and Antarctic. So there's early study by Lau et al. And mainly address the interhemispheric connection of Asian monsoon. And later on, in recent years, there is an emerging interest in looking at Asian monsoon, Antarctic climate. And for the American monsoon, Atlantic sector, sadly, very few study. The only study I can find clearly addresses is Gurney and the Welders. So there are other mechanisms. For example, the global monsoon and Hadley cell. This concept was put forward by Chambers, Wang, and Ding. And this is nothing new. It's just connecting monsoon globally to the seasonal migration of the Hadley cell. So there's a lot of studies looking at the North Atlantic influence on South American through the low-level moisture transport. I feel they probably could put under this global monsoon concept. And another dynamic mechanism is a Kelvin wave generated by latent heating of the Amazon rainforest. And the earliest study I can find was Pedro's work. And at least, I think you have some work. And then in 2007 and 2008, our group and Brent Lieberman's group look at, again, these convective Kelvin wave generated by Amazon convection using observation. But this mechanism mainly operate all year round, peak in March, April, May, but it's absent during the June to August. So there's a strong seasonality here. So what's very interesting, this is my favorite work by Brent Lieberman, is showing even the Kelvin wave, convective coupled Kelvin wave is mainly confined in the equatorial region, but they can be generated or excited by the extratropical or influence from both the southern hemisphere. So this is one source that excites the convective coupled Kelvin wave over Amazon is by the planetary wave propagating from extratropical South American to equatorial area. And another source exciting the convective Kelvin wave is the Rossby wave propagation from northern hemisphere through East Pacific and also excite the convective Kelvin wave. So the convective coupled Kelvin wave over South American become a mechanism that really enable the extratropical influence it's like a springboard for them to influence the equatorial Atlantic, South American, and Africa. So there are three, I put 4 hypotheses here, but I don't really have much of a result for the 4th hypothesis. That's just inspiration for future work. So the 3 hypotheses I hope to show some result to support this is hypothesis 1 is northward cross-equatorial propagation of Rossby wave generated by diabatic heating of South American monsoon can influence North Atlantic oscillation, or NAO, during boreal summer, December to February. So hypothesis 2 is through a shallow cross-equatorial circulation forced by cold front incursion from extratropical South American can significantly influence weather and climate variability over tropical and subtropical North Atlantic during the Austral winter or boreal summer, June to August. And the hypothesis 3 is a convective coupled Kelvin wave from Amazonia can influence tropical Atlantic surface wind and sea level height anomalies, especially during the Austral fall. And in doing so, the variation of the American Amazonian rainfall, this could be excited by extratropical South American or East Pacific disturbance and can influence the zonal mode of Atlantic SST variability. So I put a lot of hypotheses there, and it's kind of probably too busy. So I want to compensate that by just give you a simple take-home message. And so the simple take-home message is I hope to convince you with evidence whether climate variability over South American are connected to the North American Atlantic, those of North American and Atlantic sector in all seasons. Especially, I want to show you the climate variability over South American can influence North Atlantic and the North American as well. So now let's look at the evidence for the hypothesis 1, that is the diabatic heating generated over South American monsoon could excite Rossby wave, which propagate across equator to North Atlantic, and that could influence the NAO during the boreal summer. So first of all, let's look at the circulation pattern associated with NAO. So this is a schematic showing positive phase of NAO, and you have this cyclonic, anticyclonic circulation over the subtropical Atlantic, middle latitude subtropical Atlantic, and the cyclonic circulation over the high latitude Atlantic, North Atlantic. As a result, you have a drier climate over the southern Europe and northern Africa, and the more stormy weather over the northern Europe, as well as the high latitude North American, east coast of North American. So to in order to study the influence of South American on NAO, we first have to remove the Pacific influence because the tropical Pacific convection could influence both. So to do so, we actually use, first of all, we use SVD to remove the Pacific influence from the circulation over the North Atlantic. And then we look at whether we can still get the signal. So on the left side, this is the regression between these reconstructed data with the Pacific influence removed and for the positive NAO phase. And the top is a stream function over North Atlantic. And you can see these anticyclonic and the cyclonic circulation over the North Atlantic, and which is resemble to the standard typical circulation pattern associated with the positive NAO phase. And this is the quick scat surface wind regressed with the NAO index. Again, Pacific influence is removed. And I apologize for the messiness, but you do see signal that is consistent with upper tropospheric signals. And this is a regression with a negative NAO, and you see a pattern that is resemble the circulation pattern over for the negative NAO. So now we can look at the connection between South American monsoon rainfall and the North Atlantic, the NAO signal. So here, the domain we use for, this is a SAM rainfall domain, we use a trim rainfall with the Pacific influence removed for DJF 1990 to 2008. And so this is a regression between the SAM rainfall anomalies, and that is beyond 1 standard deviation, the strong rainfall anomalies, and the stream function, 200 hectopascal stream function with Pacific influence removed for positive NAO phase. So this is a 2-day, the circulation over North Atlantic 2 days before strong rainfall anomalies over SAM region, and this is a 3 after. So the main thing we look for whether the SAM rainfall could influence NAO is to look at the difference between the pattern before and the pattern after. So this method was being used by Wallace in the 80s. So you can see there's a clear difference. So 2 days before, the signal is not resemble to any positive NAO at least. So 3 days after, you see this is quite clear circulation response. This is anticyclonic and cyclonic 3 days after the increase of a SAM rainfall. So the difference here suggests that strong positive SAM rainfall anomalies tend to give you a positive NAO-like circulation pattern. Because this is a positive NAO phase, so it tends to enforce the positive NAO circulation pattern. So now if you look at the negative NAO, and the before and after pattern are pretty similar to each other. And so this suggests the influence is not, at least not clear in this case. So it is a phase dependent. And so because we can only detect the possible influence for positive NAO in the upper troposphere, so now we look at the surface, only for surface wind response, only for the positive NAO phase. So this is a scatometer, the quick scat surface wind regressed with a trim rainfall. This is a 2 day before the peak of trim rainfall anomalies, 0 day, the simultaneous, and this is 3 days after. And you see these anticyclonic circulation anomalies over the middle latitude, subtropical Atlantic. and that is consistent with what we see in the upper troposphere, which is derived from the UNSAP CFSR. It's a newer version of the UNSAP reanalysis. So therefore, now if we look at the, if we use barotropic model to see whether the diabatic heating or the upper divergence over some region could generate barotropic raspberry wave propagation across equator. So this is one test where we use the monsoon heating here and the January mean flow. In this case, we didn't even separate positive or negative NAO. It's just climatological January. And you can see these wave trend coming from South American. They're not identical to what we observed, but there are so many differences between observation and this very simple model. But generally, I think this model show that it is possible for cross-equatorial wave propagation in response to the summer rainfall. So therefore, based on this result, we feel they are tentatively support the hypothesis 1. And furthermore, we found that this effect seem to be mainly, we can only detect them for positive NAO phase so far. So the negative NAO, during the negative NAO phase, we don't see as clear signal as this, but on the other hand, we haven't exhausted our, we didn't really, haven't gone through very careful, or there's a lot of analysis we need to do to confirm that. So now the hypothesis 2, now I want to focus on the austral winter. That was austral summer, so austral winter. And austral winter is the season when seems all other dynamic mechanisms we know does not operate. For example, the convective coupled Kelvin wave, you don't see them in the austral winter, and the cross equatorial planetary wave doesn't work in the austral winter. So previously, we really think during the austral winter, there's interhemispheric interaction probably doesn't exist. However, I want to show you a result to suggest even the interhemispheric connection, these dynamic mechanism doesn't work in the upper troposphere. In the lower troposphere, and this in the South American weather disturbance can influence the North Atlantic through lower tropospheric connection. So here we're looking at an extreme cold front incursion over South American. So this is an example, how do we define extreme cold front incursion? And this is one example in 2010. And these are the temperature anomaly associated with a cold front incursion. And so this is impact. This is right, the south of the Amazon is pretty deep in the tropics and causing many casualties in livestock because of the cold weather. So the cold front incursion has been studied quite extensively in the literature, but how they influence North Atlantic has not. So here, because our focus is their influence on North Atlantic, in addition to the standard cold front incursion, we have to add extra conditions to look at these very deeply penetrated cold front into the tropical South American. So to identify those events, so the cold front incursion event is identified by pretty standard method. The sea level height pressure is higher than 1020, and we also add another condition, and as in the end, full top 10% of the higher sea level pressure events. And then on top of that, in order to detect a deeper equatorial incursion, we actually we actually select the event by looking at the cross-equatorial flow, southerly cross-equatorial flow greater than 2 standard deviation. So this cross-equatorial southerly flow is very similar to the northern Andes low-level jet showed by Charles yesterday. So, and then we also have to have another condition, which is a 200 hectopascal zonal wind over southern hemisphere. Amazon is weak westerly. This enables the cold front, the raspberry wave, propagating equatorward. So the cold front can penetrate deep. And so this is the composite of the temperature, standardized temperature anomalies over 800 hectopascal geopotential height. So the blue here is cold, exceed 1 standard deviation. The red here is warm, exceed 1 standard deviation. The contour here is OLR and indicate the convection. So that's on the left panel, so left column. So you can see 2 days before these cold front events, and these this cold front coming from South Pacific, and 1 day before, and then the 0 day, that's when we define the extreme cold event. And you have a very cold temperature anomaly, more than 1 standard deviation over much of the South American. And so this right column shows the contour here shows the 800 hectopascal geopotential height. And the shade here shows the anomalies 800 hectopascal geopotential height. When you see red and blue, that means exceed 1 standard deviation. These are all standardized. And then the vector here shows 800 hectopascal geopotential, the wind anomalies. So what you can see here is associated with these cold front events, and you see a very high pressure increase of geopotential height more than 1 standard deviation over tropical and the subtropical Atlantic, in addition to South American. And this is 1 day after these cold events and 2 days after. And you can see a wide spread of increase of low-level geopotential height over the tropical and the subtropical Atlantic. So now we zoom into the North Atlantic subtropical height, the impact of these cold events. So this is a climatological location of the NASH, or North Atlantic subtropical high. The shade here is 1 standard deviation. And what you can see here is associated with these cold events, 2 days after, the NASH is expanding significantly more than its climatological location, and also expand westward. And so if you look at the bottom panel, the 200 hectopascal geopotential height level, and what you can see here is there's a strong, this is day 0, strong equatorward propagation of the raspberry wave, but they're limited to the southern hemisphere. And there's no upper tropospheric signal in the northern hemispheric part. So what caused the expansion of the NASH over North Atlantic subtropics? So to explore that question, we look at the vertical and the latitudinal composite of the standardized geopotential height, and that's a shade. And red means higher pressure, blue means low pressure. So when you see red, that's close to 1 standard deviation or above. So what you can see here, and then this curve these lines are the streamlines. So what you can see here is this is a day 0, the cold front incursion. So you can see this northward advancement of these very high pressure and the cold front, and they move only, so the upper tropospheric signal is limited in southern hemisphere, but in the low troposphere, this very cold dense air actually overspill from the southern hemisphere to northern Atlantic, northern hemisphere, and all the way actually to 20 degree north. And this is 1 day and 2 days afterward. And the return flow on the warmer side of this front in the middle troposphere and coming back to southern hemisphere. So this is really a cross-equatorial shallow meridional circulation induced by this cold front that enable them to influence the North Atlantic subtropical height. And so this is a summary of the result. So the influence of a extreme cold front incursion over South American on the north, subtropical North Atlantic are really carried out by two mechanisms over the southern hemisphere, and this is a deep equatorward penetration of the cold front enabled by the propagation of the raspberry wave in the southern hemisphere. But this only can go as far as southern hemispheric side of the South American. So for from the equator to North Atlantic, the influence is carried out by the lower tropospheric meridional circulation induced by cold front. So the implication to North American monsoon here, even we haven't looked at it directly, it's well documented that the North Atlantic subtropical high has influenced the North American monsoon. One is they're leading to middle summer drought over the north for the Name region. Also, they lead to early demise of the Name. And so therefore, the implication here is this extreme cold front incursion from extratropical southern hemisphere, South America, could intensify the NASH and also lead to westward expansion that could potentially affect the North American monsoon. So the hypothesis 3 is the convective coupled Kelvin wave from Amazon can influence Atlantic sea surface wind, sea level height, and the sea surface temperature. And in doing so, it affects the tropical Atlantic variability, at least the zonal mode. So the convective coupled Kelvin wave was, as I mentioned earlier, was actually studied for decades. And so these are example of observational example of this Kelvin wave. So here is a trim rainfall. We didn't even need to do, the signal is so strong, we didn't even need to do the filter. You just plot a map of the trim rainfall, and you can see this eastward propagation of the rainfall signal associated with this convective coupled Kelvin wave originated from the equatorial Amazon. So we can also do the composite of this rainfall signal based on follow these based on the phase of these Kelvin waves, and this signal has a very clear matches Kelvin what we expect from the convective coupled Kelvin wave. It's about propagating speed 15 meters per second, and the zonal wave number 6, period of 6 to 7 days. So these clearly show that these Kelvin waves generated by Amazon convection can influence the ITCZ over the Atlantic. So now let's see how they affect surface wind, sea level height, and the sea surface temperature. So these, again, is the Hofmiller diagram. This is longitudinal and time. So what you can see here is episode of these convective coupled Kelvin wave originate from South American and propagating eastward with time, shown by trim rainfall. And this is associated surface wind anomalies detected by QuickScat. And you can see associated with these convective Kelvin wave, and you have these westerly anomalies. or you can call westerly bursts over the equatorial Atlantic. And this is a sea level height change anomalies and based on JSON satellite. And you can see these positive anomaly of sea level height, and that's the indication of the ocean, the Kelvin wave over oceanic Kelvin wave. And then this is the sea surface temperature. So associated with this episode of these convective coupled Kelvin wave, you see westerly wind, you see increase of sea level height, and you see change of sea surface temperature. And after this event, the sea level height over eastern equatorial Pacific changing from lower, the sea level height you can see was higher over the west and now was higher over east. The SST from cold transition to warm. So this is an example of onset of Atlantic Niño. And so we also look at the undersurface signal, and that's consistent with what we see at the surface wind and sea level SST. So this is a Parata buoy data. So we pick 3 stations from western equatorial Atlantic to central to east, southeast Atlantic. And what you can see here is the thermal climb depth was tilted with deeper in the west, shallow in the east in the January, February, March. And then after these coupled convective Kelvin wave in March, April, May, and the sea level height, the thermal climb slope changing. So now it's deeper over east, deepened over east, becomes shallower in the west, and that's consistent with this SST. So all these signals from subsurface to surface point to the onset of Atlantic Niño induced by these convective coupled Kelvin wave originated from Amazon. And so this is just to further drive message home. We actually use the observed wind and to drive a HICON model. And you can actually see this changing of sea surface temperature and thermal climb that is changing with the, driven by these observed surface wind. And this is a same model experiment. Now we're actually driven by the wind associated with convective coupled Kelvin wave. And the similarity between these two experiments suggests the signal is really induced by convective coupled Kelvin wave from the Amazon. So this is just composite for more events. The result I showed previously is for one case, and this is composite for at least the six Niño, Atlantic Niño events. So you can see the signal even when you look at the composite. So how does Amazon rainfall variability affect the Atlantic Niño? And to explore that question, we actually did a composite. So this is the Amazon raining season, late ending of the raining season, and means you got more rainfall, you have a more frequent, stronger convective Kelvin wave in the boreal, in the austral fall, and then you see few months later the austral winter onset of the warm phase of the Atlantic Niño. So when you have a early ending of the Amazon rainfall, you will have a less and weaker convective Kelvin wave in the austral fall. And usually that followed by cold phase of Atlantic Niño in austral winter. So this suggests that the variation of the Amazon raining season demise could contribute to the cold or warm phase of the Atlantic Niño. Okay, I'm trying to wrap up. So this is hypothesis 3 I think evidence so far support the influence of South American rainfall on tropical Atlantic, and in particular the onset of the Atlantic Nino. So what is the broader implication of this result? So if we look at the literature, we know that Atlantic Nino is being connected to Pacific Nino. And so this is a famous paper by Ping Chen in Nature, where they show this connection. This is a correlation between Atlantic SST and the Nino 3 index. So what they show here is, what they suggest is El Nino influence Atlantic Nino, influence SST here, and through the meridional mode, they can trigger the onset of the Atlantic Nino. But they acknowledge that they can only half of the Atlantic Nino can be connected to El Nino. So what about the other half? So here, I think our result suggests that we actually look at all the Atlantic Nino events within the record we have, and we can link almost all the Atlantic Nino onset with the late wet season ending of the Amazon. So I think our result provide another mechanism, at least, to show that the Amazon convection actually has played a very important role in trigger the Atlantic Nino onset. So this is a summary and take-home message. And again, I want to emphasize that over the Pacific, where most of the cross-equatorial teleconnection research is focused on, and those teleconnections mainly occurred in one season, that is a boreal summer. Over the Atlantic and American sector, the cross-equatorial influence actually happened in all seasons through different dynamic mechanisms. And so besides this cross-equatorial raspberry wave propagation in boreal winter or austral summer, we have a shallow cross-equatorial meridional cross-equatorial circulation that connect South American influence to North Atlantic through the in the austral winter. And in the other seasons, such as the Austral 4, the convective coupled Kelvin wave enable extratropical South American or North Pacific to influence the tropical Atlantic, and that has very important influence on the onset of Atlantic Nino. And so the outstanding question here, this field is so open, and there are so many questions. And so I only gave 3 examples based on the evidence I have. And by no means the outstanding questions are limited to this. So one is the hypothesis 4. So whether the onset of the one American monsoon could accelerate or contribute to demise of the other American monsoon. So we look at it in the March to May. We don't see clear evidence that onset of a North American monsoon could link to the demise of the South American monsoon. But yeah, finish. Yeah, should be. So but for the September to November, the Austral spring, if we look at the connection, this is the SVD, the singular value decomposition. What you can see is the onset of the South American monsoon is quite well correlated with the circulation anomalies over North American monsoon. Of course, it's more on the east side, not the core region. But this circulation is actually moving raining area away from the core region to the east. And this mode is leading that mode by the leading regression is stronger than the lag. So that seemed to imply that onset of South American monsoon could contribute to demise of the North American monsoon. But this is a very just correlation, very preliminary. Another very intriguing question is if you look at the variation of the demise of the North American monsoon and the onset of South American, this is the Amazon, southern Amazon raining season, and their variability is very, very well correlated. So in Paula's work, she explored a few possible causes, but by no means those are conclusive, and much of work needs to be done to understand so why they're correlated and what caused the early demise of North American monsoon and late onset of South American monsoon. And another question is, we know that South American, especially the Amazon region, has been experienced a lot of changing. Both this changing can be linked to the global climate change. This is a poleward shift of southern hemispheric jet, as well as a regional changing. This is a convective inhibition energy connected to surface dryness. It could be due to land use, could be due to physiological response of the forest to the plants to elevated CO2. And these contribute to the delay of the onset of wet season. So how does this onset of wet season would in turn affect North American? And that's a question really need to be explored. So there are many more questions. And what I hope to see is in 5 years, if we have opportunity like this, and there will be many papers we can review in literature, not just my work, but work from the whole community. And I will end from here. Thank you.
Okay, let's go. Okay.
So in regards to the first hypothesis, the idea that anomalies in South America influencing the NAO, there are a few papers that show that the MJO connects to the NAO. Do you think it's possible that when the convection associated with the MJO is propagating along the equator and gets to the South Pacific convergence zone and triggers the wave train, and therefore connecting to the, so inducing anomalies in Brazil, and that is connecting to the NAO?
Yeah, we actually remove the Pacific influence. And so by remove the, we use SVD to remove that. So all the mode that connect to Pacific convection derived from TRIM and the North Atlantic wind and the South American rainfall are all being removed. And that's why I was showing these reconstructed data. That's a very, very valid question. And I'm not sure we remove them completely, but we remove them as much as we can. So hopefully the MJO, since they're correlated with convection over Pacific, hopefully remove them already.
Yes. Okay. A very nice talk, a lot of new concept to me anyway. Now you said that the Atlantic Nino or Nina seem to be strongly driven by the monsoons. I think it's a late retreat or late onset.
Late ending. This is a
late early,
austral fall.
Yeah, fall. So it's a late retreat.
Yeah.
Late retreat or early retreat. And if it is late retreat, it lead to an Atlantic Nino.
Yeah.
If it's early retreat, it lead to an Atlantic Nina, co-condition.
That's generally correct, but we actually look at every Nino event. I didn't show here because that's a very new result. We can link to the onset of Nino always to the late demise of the Amazon wet season. But La Nina version of the Atlantic Nino, Atlantic La Nina, are not always linked to the early demise of the wet season. We don't understand why yet.
Right. But so if you look at 1997, for example, 1997 we had one of the strongest Atlantic Nina, and then we then the JJA maximum Atlantic Nina. Then in the following 6 months we have the biggest El Nino of the 20th century, and these kind of connections apply to 82 as well. So 82 JJA, the Atlantic has a very strong Nina co-condition, and the reverse is again true. That if you look at 1998, the biggest La Nina, 1998 JJA has the warmest Atlantic Nina. So it looks like, it looks like the two just develop together. So if your monsoon's retreat has any precursory effect on Atlantic Nino, it will also have precursory effect on the strong El Nino or La Nina. So look at that.
That's a really great point. Actually, 5 years ago, Zheng Yuliu strongly encouraged me to look at the influence of South American rainfall on Eastern Pacific because it's a sub-sinking branch of that. I haven't looked at it, but that's that is actually extremely interesting.
Big sort of science.
Modeling result already suggests that, although it's not conclusive, Paula Nobre had a paper. They look at a coupled atmospheric ocean model for deforestation. They actually show the increase of El Nino. But then when you look at another model, like UCLA model, and they show no effect. So that's interesting. I think it's a very important topic, but modeling study has not been conclusive. Yeah. Thank you. Yeah.
How do you think that, I mean, I'm not sure if Kelvin waves can initiate the onset of the monsoon because, well, it's a fast mechanism, right? I mean, Kelvin waves are like, square propagating, but kind of fast modes. And also, I don't know if you have thought about the Rossby radius of the formation. I mean, I think it would not be that big, right, over the tropics or Kelvin waves. And also, yeah, I mean, what do you think about it?
Yeah. So your question is, Kelvin wave is very fast event. How could that affect climate, right? Slowly.
Yeah, I mean, because that's basically for the hypothesis one. I mean, something like the monsoon, it's going to affect the North Atlantic Oscillation, and they are on different time scales, right? So it's like, so I think it would be the same for the Kelvin waves in the sense of the monsoons, and maybe I think that MJO could be another.
That's a very, very good question. Here there are two things. One is for the Kelvin wave, even their signal is short time, but it's very well established in literature. For El Nino, these westerly bursts played a very important role in trigger the El Nino events. So we use those mechanisms can be explained by these convective, how convective Kelvin wave affect Atlantic Nino. Another way of influence is it's not one Kelvin wave events trigger the Nino. It is frequently westerly bursts repeatedly kicking the system that trigger the Nino. In terms of Rossby wave influence on NAO, we have to focus on short time period to detect a wave signal using observation. But you can view that NAO has a short-term variability, has long-term variability. Increase of frequency of short-term variability in one phase actually gave you these low frequency variation, contribute to low frequency variation. So on the climate scale, I think these effects should also work, except when you use observation, it's hard to isolate them, right? Once you look at long-term scale, the SST, all other influence also contribute to the signal, and we cannot separate them use observation.
I'm confused with one of the conclusions about the early demise of the North American monsoon. You mentioned the cold fronts and the expansion of Nash. But it is well known that when Nash is expanded or is strong, it's associated with wetter North American monsoons. And that's linked to the negative AMO. So why do you conclude that it's an early demise of the NAM?
Yeah, thank you so much for this question. I didn't clarify. Name is, there's a broader name region, there's a more core region. So the core region that Francina mentioned, maybe you focus on, is on the west side of the Mexican, the Sierra Madre, right? In our case, all the signals are on the east side. So, yeah, and even include the Gulf region. So that means these because they're anti-correlated, like Francina, yeah. So early demise here means more on the core, in the core region. I should clarify that, yeah.
What's the way to put it?
Yeah, we don't see much of a signal in the core region. I think it's just too far from the South American. Yeah, thanks so much for. Yeah.
Could you? I have a very quick comment. Could you go back to the hypothesis 3? No, a little bit more. So the Atlantic Nino. You had these composites.
Oh, here.
Atlantic Nino and Nina.
This one. No.
Well, one, you had isolines.
Oh, this one?
Of these composites. So, but you can go to this shaded composite as well.
Here, which one?
Okay. No, the other one that wasn't. No, the other. No, the composites of Nino and Nina, Atlantic.
Yes, yes. Oh, this one.
It's okay.
Yeah.
Okay. Well, if you look at these composites, actually you can see, and you had another composite, I think with isolines, where it was clearer. The maximum was near in subtropical Africa. So it characterizes, and here you can also see this.
Yeah.
It was even further south, the maximum, in this other composite. It characterizes this Benguela Nino. And, well, we did some work with Chris Reason about the influence of convection over South America and the Benguela Nino.
Okay.
And in this case, you have, yes, this equatorial teleconnection, this Kelvin waves, but also very strong extratropical wave train that induces oceanic circulation, superficial circulation, that causes these strong SST anomalies in the subtropics.
Oh, okay. Which paper? I need to read.
It's in Journal of Climate 2011.
Okay. I am definitely
The relationship between the Brazilian South America convection and the Benguela Nino.
Okay.
Where these strongest SST anomalies are more to the subtropics here, as you see there.
Yeah.
Okay.
Oh, okay.
Well,
Yeah.
thank you very much.
You're welcome.
And now we'll have the presentation by Maria Assunção Silva Dias on diurnal and local variability of South American monsoon with possible effects of aerosol. So it's higher frequency variability of the South American monsoon. If you want the camera to follow you. Yes.
This. Good morning. Thank you, Alice, for inviting me to give this talk. I will start by changing scales from the previous talk and by asking a rhetorical question: how well do we understand and how well do we forecast rainfall, short-term rainfall in the South American monsoon? So we've seen in the previous talks yesterday, we saw climate models that roughly represent rainfall over South America. Yes, and the details. When is it going to rain? Morning, afternoon, night? Is it going to be downpouring rain? Or are we going to have a thunderstorm with lightning and winds? And if you've ever lived in this region, you know we're not doing a very good job on this. From, let's see, is this pointing to something? Oh, the other side? No. Is it pointing?
Yeah, there is a pointer here.
Oh,
So,
here.
Yeah, and just don't
Mm-hmm.
get the fingering.
Okay. So, and I'm talking about what happens in the extreme northwest, but I'm going through the whole region, even São Paulo, where we have more technology and everything. So it's a big question. How well do we forecast rainfall and how well we do the details of intensity and timing? So the understanding part, we've done some work on that, and I'm going to focus on two big experiments, the LBA that had very intense campaigns in this region, and the Go Amazon that is around Manaus. And I'm going to focus on some of these things that happen in this area. And I should change this. Yeah, so I'm going to talk a little bit about diurnal variability, mesoscale convective systems and cyclonic vortices that we see in the region, and the potential effects of rainfall. For the diurnal variability, there are many papers. Most of them started with LBA, and there's a 2002 JGR special issue that has most of them. And Go Amazon is already providing some input into this. So this is one of the first by Luis Machado, 2002. He looked into just 2 months of data, basically, the LBA wet AMC and TRIM campaign in Rondônia, southwest Amazon. This down here is a radar, more than 10 dBz, 20 and 30, just to separate intensities, with peaks in the night and in the afternoon. And here's the same sort of thing, but for satellite. So we see for different temperature thresholds, this afternoon peak is delayed in the satellite because it's the time it takes for the grow up this big anvil cloud and give you the view from space. This is for one region. Luis Machado also looked into other places, separated wet season to dry season, and looked into the cloud fraction as seen from satellite. Open circles is total cloud cover, and black circles is just the cold cloud cover. And I'll just call attention to a few things. Everything is local time. The dry season in Brasilia, Brasilia is right in the middle of the region. In the dry season, you have almost no variability, and it's very well defined in the wet season. Vilhena also has a very well defined, it's in southwest Amazon, a very well defined dry season, so the dry season cloud fraction is not variable, but in the wet season, yes. You go to Manaus and Belém at the core of the tropics of the equatorial region, then you have diurnal variability all the time. Go Amazon looked into things close to Manaus. It's just 70 kilometers east of Manaus, the city of Manacapuru, where there was this very sophisticated network of instruments, vertically pointing radars and LiDARs and network of rain gauges. This is just the rainfall rate for the dry season, the wet season, and all. They stayed there for 2 years, 2014 and 2015, with continuous measurements and a few intensive periods. This is, you can see the rainfall rates are much lower in the dry season than in the wet season. Here it's for all days, and this is just the rainy days. And this here is for the totals. How much does it rain? So you can see the things goes to 200, 300 millimeters, and since the wet season, you're reaching 200 millimeters in some cases. And this is the convective fraction. Convective fraction is what? The part of the convection, the rain that's really convective, and it's basically around 80%. They also looked into details with this pointing LiDAR and radars and everything. They were able to classify clouds. Here we have shallow clouds and cirrus, cirrostratus, congestus, deep convection, altocumulus, and altostratus. This for the wet season and this for the dry season. So this is where you see the largest difference. The dry season, you still have congestus, but much lower frequency. You still have deep convection, but still much less frequency. Things pick up in the afternoon here. In the wet season, there's this peak in the afternoon, but there's also the night peak. And if we go ahead and look into a network of weather radars, this is an incredible network. 10 weather radars looking into the Amazon convection. They are spread over the area. They belong to CIPAM. And Ivan Saraiva took the opportunity that he was working there and cleaned up 5 years of this radar data, 2008 to 2012. A very nice database to understand what's going on in the Amazon. So one of the things that he showed with this is if you have radar, you can separate what's convective and what's stratiform. So he did that for each one of them. Each one of these little boxes, here you have local time. Local time varies a little bit, an hour, but for each one of them, it's local time here. And here's from January to December. It's the annual. So you have the hourly and the annual cycle in the same figure, and then you're looking at frequencies. So one thing that you see when you look at that, see convective. Convective, you have convection almost all the time, but there are breaks, like if you go here, Cruzeiro do Sul. Cruzeiro do Sul is this one, the extreme, the most western radar. It has a very well-defined break in convection in winter time, or the dry season, right? Another thing that you see here, looking at convective, is the nighttime maximum. There are places where it's non-existent. This one is Belém. Belém has very nice convection. This is the coastal convection that often triggers squall lines that will propagate throughout the Amazon. It has a very well-defined January, February maximum. Then there's another one a little bit further on, May, June, but you still see convection all the time up to the whole year round. Santarém, which is this one, Santarém is here. It's just downwind from these squall lines that form near the coast. They reach Santarém at night, and then you can see the frequency of these things. They are also stratiform. They have a very nice stratiform presence in the area. And so on. So what this thing tells us is that convection is different across the Amazon. Different places, different regimes, because different systems are happening in each one of these places. Like Boa Vista, we don't know much about how Boa Vista is here. It's in the northern hemisphere. Most of convection is in August, September. It's very different from everything else. So the main message is that we're used to talking about afternoon maximum of rainfall, but this is just an average picture. The real picture is of strong variability and systems that form in different places. And if we break the data in easterlies and westerlies, like in SACs, South American convergence zones, and non-SACs categories, we'll see also some differences. This, when you have the westerlies, you call it the monsoon rains, and when you have easterlies, it's a break phase. Here you see in shaded the anomalies, positive anomalies over all this region in the westerlies, and negative here. This is a work from Charles and Leila. And the opposite in the easterlies, the break phase. More rain here and less here. Rondônia was sitting right in here. This little box that you probably can see. And here is what we see as a rain rate sitting in Rondônia with a westerlies and easterlies phase. A succession of westerlies and easterlies. And here is a smooth version of all these peaked daily rainfall rates. So easterlies is where you have more intense rain, higher rain rates. Westerlies, not so much. If you look into the diurnal cycle of convection, during SACs or westerly flow, these are different authors, but similar results. This is the total rainfall diurnal cycle, and then here you have the convective and the stratiform part. Here's for the westerlies, and here's for non-sacs. The break phase, the easterly flow, much more peaked. It's a much more intense diurnal cycle. So the picture you get is you have monsoon rains, it's raining all over the place, and you have a more smooth diurnal cycle. As soon as you get into the easterly phase, you just have a few places where it's raining, deep convection, and lots of convective systems. This is northwest tropical South America. This is a sequence of daily anomalies of convective systems, the number of convective systems. Here's, look at this, a very well-defined easterly phase, a break of the monsoon, lots of convective systems. It seems like a contradiction. Monsoon is where it rains. When you have a break, it doesn't rain. Oh, that's the trick. It does rain, but different. It's a different rain. And from the very beginning of LBA, Earl Williams was with this flag during the westerly regime in the wet season. This is the number of lightning strokes. So most of the time you had strokes that were under 1,000, say. You get into the easterly phase, you shift, you start having lots of storms with lightning. Lightning is an indicator of deep convection, a thunderstorm. Lots of ice. It's a thunderstorm. No lightning, a little bit of ice and gentle rains. It can rain, it can pour rain over the area. It can rain as much as in the other case. However, it's different. It's a different type of rain. One is a thunderstorm, and the other is just rain, right? And he argued that when it's polluted in the pre-monsoon, you have more severe storms and with more lightning, etc. We'll get into that a little bit more afterwards. We're still looking at some other things of this wind regime thing about the northerly part. Rong published this very nice paper on the cross-equatorial flow. Winds from when the IV index, the meridional winds were from the north, you had lots of rain in South America. And when they were from the south, the rain shifted to the northern hemisphere. What we saw when we looked into one of the radars, São Gabriel da Cachoeira, is in the extreme northwest. When the winds are from the north, here, what we see is, again, time of day and month. Those are from when the winds are from the north, and these from the winds are from the south. Here we show the frequency of reflectivity seen by the radar going above 20 dBz, and here 40 dBz, and here the number of lightning flashes. If you look at this, the winds are from the north, very oceanic, very moist. Here the winds are from the south, they are a bit drier, more polluted, different air masses. Here is where we have the thunderstorms and more flashes. So this is work in progress. We're exploring this data with this idea, but the message is that the wind regimes also change how convection evolves. Okay, let's look at mesoscale systems. Several papers. Let's start with one category of the mesoscale convective complex. The mesoscale convective complex has to be circular, has to live more than 6 hours, that has to have an inner core very cold. It's a very organized system. It's a category. the more well-organized systems. First one that looked into that for South America was Inés Velasco and Michael Fritsch. They looked into 2 years, 1982, 1983. They already pointed out that 1983, an El Nino year, there were much more mesoscale convective complexes than in 1982. That's probably because of the upper level jet. And after this, we see, for example, Durkee and Mote. They only looked from 10 degrees south to south, but they looked into 10 years. And these are the locations of the MCCs they found. And they also put the location of the low-level jet, the more frequent location of the low-level jet over this area. So you can see a close connection that's been in many, many papers. So the rains in this monsoon area, these are all warm season rains from October to May. So they are not just uniform, they are composed of mesoscale convective complexes. Other people like Conrado Conforti had a look in other years and found MCCs elsewhere also. So very frequent. When you relax the definition of the MCC and just say, well, let's look at the systems that last as long as they last, can be short-lived or long-lived, and they are, there's the isotherm in the infrared image, the 235 isotherm is closed, so you can define a system. You follow this. There's a recent work by Amanda Ribin and others for the Go Amazon, where they looked into the number of MCSs over the Amazon basin. And here you can see these, the red ones are the short-lived, the triangles blue are the long-lived over the years, 2000 to 2013, and this is the total, and this is the number of them. Of course, they are counting, they may be counting same system several times because it can come in different images. But anyway, it's to give you an order of the number of MCSs. You're going here to 8,000 sometimes. When are they seen? They mostly seen over January to June, maximum in March, April. Again, these are the long-lived and the short-lived and the total. And how long do they live? So here we have hours, duration, number of occurrences. The short-lived are the ones that live less than 6 hours. And the long-lived are the rest. So you can have MCSs that live more than a day. And ones that are used to tropical Amazon weather are probably thinking that these are the squall lines that form on the northern coast. They can propagate throughout the basin, and sometimes they go over a day or two. They can propagate through the whole basin and die near the Andes. So these are the long, very long-lived squall lines. Very rare, but they do occur in the region. During the day, when do they happen? This is the time of genesis, maturation, and dissipation. Genesis, the blue thing here. time UTC, this is remove 3 hours, so it's just afternoon, after 12 to 15. And then maturation, end of the afternoon, and dissipation can be along the day. Okay? Those are the short lifespan, these are the long lifespan. And these are the trajectories of these systems over the months, over the several months. The length of the arrow means how long did it travel. And you see a few things that as soon as you look at that, you look for the largest arrows. And they are here in the winter, associated to systems that cold fronts and things like that. But what you see basically during the warm season is that this propagation from east to west and then north to south and then back. That's the typical propagation of these mesoscale systems. And some of those, these are, well, you won't be able to see. Speed is the size of the arrow, the thickness of the arrow. Most of the ones in the north, they have speeds larger than the wind speeds. They are not just not carried out by the wind. They are just propagating with a dynamic, a mesoscale dynamic mechanism. Okay. In a more simplified sense, Luis Machado looked into the MCS for this the LBA campaign. And again, these are MCS propagation speeds and directions. You can see this propagation using the 235K isotherm. Here for comparing 235 with 210, which looks just at the coldest cores, a little bit of difference. And here for the easterly and westerly regimes. On the easterly regimes, much larger arrows than in the westerly regimes. More stationary systems. Here is Rondonia, basically. More stationary systems here than here. Well, it's a general rule. And the 2 years of Go Amazon, they it's one of these unlucky things. You go to the field with all these things, and you get a year with not so many MCSs. Like climatology is blue, short lifespans and long lifespans. Climatology in blue, and what happened 2014 and 15 is this. So they were very calm years, and you wanted to have all this very strong convective systems so you would be able to measure them. But anyway, that's how it is. Okay, let's look at cyclonic vortices. Cyclonic vortices, you can see them embedded on the South Atlantic Convergence Zone. Here, it's a work by Mário Quadro. Here, this satellite image showing this system. Here, you look into a downscaling using BRAMs from large-scale reanalysis. The reanalysis actually does have a sort of a circulation, but the downscaling show a closed circulation. This is low levels, 2,000 meters above ground level. And here in another time. These systems, they have vorticity anomaly, negative vorticity anomaly in low levels, here, colder than the environment, and they can last for some time. As soon as they become vortices, usually the life cycle reaches a day or more than a day. But they are embedded in the South Atlantic convergence zone. You can find them by an automatic detection algorithm. This was done by selecting days with the South Atlantic convergence zone. And within the cloudy region, we would look for a minimum value of relative vorticity, and then look around and see if the winds were turning clockwise with some freedom, but the winds had to turn clockwise to define the vortex. So we used 10 years of South Atlantic convergence zone occurrences. These are the years and the days of the year. So these are the several cases, and there were 43 cases, 43 days. And here's where we located MCVs. The colors indicate if a given center can be seen in a different level. Like the red one means 2 levels were found that had one over the other detected an MCV. There's one here with 6 levels, a very deep one. So they are spread over all this area. This area is, well, this is called the continental Amazon region, continental coastal and oceanic. So they are all over the place, always embedded in the South Atlantic convergence zone. So they are anomalies along the South convergence zone, places where it will rain much more than in others. Separating these 3 zones, the Amazon, the coastal, and the oceanic, and counting the number of cases in each time for the reanalysis, for each time of the reanalysis. This is UTC, so remove about 3 hours, average 3 hours. So they can happen all times. The Amazon ones, this is 12 UTC, is early morning, most of them, early morning, so it's not just triggered by surface heating. The coastal, most of them are late evening. 0 is 9 in the evening. So probably something that happened, some convection during the day that evolved into a vortex. And the oceanic ones are again early morning. So we can do downscaling from the reanalysis and find them in places where probably topography, sources of moisture, but forecasting them beforehand. Oh, I would like to see one that you really did a good forecast. Anyway, let's go into possible aerosol effects on rainfall. We'll look a little bit into large-scale dynamics, radiative effects, and cloud microphysics effects. Aerosol in the Amazon and in most of South America, in the South American Monsoon region, the basic origin is biomass burning. Biomass burning peaks in the dry season, but spreads also into the transition mainly, and a little bit in the warm season. If you go into the Amazon, there's the Amazon, a very deep Amazon, where nobody goes really because it's so wet, so many trees. not even deforestation will go there, because then you can move machines. They will get stuck in the mud. So that's the very core of the Amazon. But in the fringes of the Amazon, there's people, there's civilization, there's urban centers, there are places where you burn things, where you make coal from wood. So a whole year around, there are sources. The Amazon is not this very unpolluted place anymore. But in the dry season, things can peak very much, and some years more, some years less. We could argue here for some time whether this is because here there were no forest police going there and enforcing the no burning, and here, yes. Or it's climate. Was it raining more here than here? Well, we could go on for some time over that. But the thing is, there's a very strong seasonal cycle. At the beginning of the rainy season, there's lots of pollution around. The transition from dry to wet season is where aerosols and clouds interact. It's the main place. And when we talk about aerosol effects, we could be talking about radiation, just how radiation gets scattered back to space and doesn't reach the surface. That's the radiation effect. And we could talk about cloud microphysics, how the clouds evolve. And warm clouds, we're quite certain of this diagram, increase concentration of aerosol, and rainfall reduces to zero. It's the difference between a cumulus cloud over a continent, polluted continent, and the one over the ocean or over the green Amazon, the unpolluted Amazon. The shallow clouds do rain, but over places where you have lots of pollution, shallow clouds, the warm clouds, do not rain at all. You go into deep convection, and then this is a mess. There are all sorts of things happening. You increase aerosol concentration. Initially, you could increase rain and then decrease. But where? You could increase it up to this point and then decrease. This is for simulations for the Texas clouds. This is for a gate cloud. So environment plays a role in deciding whether pollution will affect rainfall by increasing it or by decreasing it. So the pollution spreads over a region. These are trajectories. Colors mean the trajectory. These are convective trajectories. As soon as they find a place with clouds, they will go up. So this is the work of Saulo Freitas and Carla Longo. They've been looking at this. This is for August, this is September, a variety of trajectories, starting here and then crossing to the Pacific or going south and going to the Atlantic, upper levels. This is a case where going south, it found a cold front and then went up and then went back. So all sorts of possible trajectories. The thing is, these are the spots where you have burning this particular year. Burning means you get a pyrocumulus over the burning. Pyrocumulus is a cumulus that forms over a fire. Then this thing gets into upper levels and then spreads. A regional smoke plume like one we are having right now. It's on the newspapers. Right now we have a smoke plume that leaves these regions and goes south, and it can go over São Paulo, over Paraguay, Uruguay, Argentina. So, and usually it's not at the surface, it's at some level Rong Fu and Zhang looked into the effect of biomass burning aerosol using reg CM3. And they compared for September 2002, a transition month, month that we were measuring stuff in Rondônia. So there are two simulations, one control with no aerosol, and then here we see the aerosol simulation minus the control. This is difference in rainfall for the whole month. This is for pressure, for low level potential temperature, lapse rate, and here for pressure. And here's the vertical velocity. The pressure is interesting. It's a high pressure. So high pressure, more stable, less rain, or few places with less rain. This means basically a delay on the onset of the rainy season. That was one of the conclusions of the paper. A large-scale effect of this. If you look into other work on that with Brahms, again, looking into all the biomass burning spots and the spread of these, here is the satellite aerosol optical thickness spreading to the south. And here's the model, how does the job that it does, very similar. And then you look into radiation at the surface and the difference in temperature. You have a negative anomaly of 3.5 degrees at the surface. Another work by Rong Fu, they transition as seen by ICMWF era. At this time, they didn't have era, or did they? So here, it's a transition from dry to wet season, where the main point of the paper is that the transition is triggered by an increase in latent heat flux at the surface. But then, when you compare CMWF is this, and these are the observations, the lower latent heat flux in the observations may be an indication of the aerosol effect. So the aerosol effect is something that can really potentially affect the onset of the rainy season. Perhaps what Elisa Sena showed yesterday, some of the explanations for the delay of the onset of the rainy season is basically aerosol. And finally, microphysics. The time we were looking at that is the transition from dry to wet season, where you have a strong decrease in concentration of aerosol. We flew over these places here and these arrows and measured cloud microphysics. And basically, blue ocean, green ocean are very similar. You have lots of big droplets. You fly on smoky and pyrocumulus, you don't find the big droplets. You find lots of small droplets. So very different cloud condensation nuclei. The same is seen in the most recent campaign, the Chuva Acridicon campaign. The same thing, polluted, very peaked cloud droplet distribution. When you go into Amazon background, you get big droplets. So very different cloud microphysics in these two cases. And if you use these different cloud droplet distributions in a model, just change the cloud distribution, just that. Everything else is the same. The clean one produces this type of rain. This is horizontal direction, this is height. So the very clean, you start polluting it and go to this. Start polluting it, you start getting more vigorous convection. So the effect of increased condensation, cloud condensation nuclei can change the character of deep convection from something that's, it will rain a lot. This thing will rain a lot. It stops 400 millibars. But this one will be severe. And this is something that's been known for a while. The relationship between ice-water path and flashes is almost a straight line in this kind of diagram. If you look into the monsoon, the South American monsoon region in the December to February season, the number of flashes is very low, very deep into northwest Amazon, and is large to the southeast. If you do the same in the transition season, you will see an enormous amount of flashes all over the place. So very deep convection, very strong convection with lots of ice. So back into Earl Williams' aerosol hypothesis, that's basically what we're seeing. Basically, if you have a clean atmosphere, large droplets form and they rain easily. If you have a very polluted atmosphere, these things form lots of cloud droplets. They don't rain until they get into the ice phase, and then they have, the thing becomes a thunderstorm. So as an overall conclusion of all this I've been talking about, I was talking about being able to understand and forecast the details of convection. And I can tell you that diurnal and annual cycles vary across the region and are very sensitive to wind regimes. The mesoscale systems provide local intensification of rainfall. Aeromass from biomass burning may delay the onset of the rainy season and change behavior of deep convection from heavy rains to lightning storms. And I leave you with the questions that we need to address, probably. If the models are simulating, predicting this annual cycle, diurnal and annual cycles, and what should we do to improve short-term forecasting of rainfall in the South American monsoon? Thank you.
Thank you, Assunção. Do we have questions?
Thank you for your presentation. It was very enlightening. I'm wondering about the previous slide because you were discussing the role of the aerosols in the beginning. Are they cooling the surface? Are they warming the surface? And then you have this interesting phenomena that when you have a polluted air mass, you will end up with a lot of, you change the drop size distribution, but at the same time you end up with a lot of lighting. How that can happen? I mean, I'm wondering, how does this happen? Because if you have a polluted area, how this can get vigorous updrafts?
Same area. So the surface input about the same. If you have a clean atmosphere, say you have 300 ccn per cubic centimeter, this is clean. So they go up with the updraft and start forming droplets, but there are not many droplets. So they grow big, they cannot be sustained in the air, and they will fall as rain. barely reaching the ice face. If there, instead of 300, you have 1,000 or 3,000, which is common when you have a polluted atmosphere, the little droplets, the liquid droplets, will be very small. So you have this enormous amount of liquid droplets, but they don't fall because they are very, very small. So the updraft keeps pushing them upwards. They go through the zero phase, 0 degrees. They keep going, and then the ice phase, when you get into -10, -20, you start having the ice phase. And the ice grows very easily because of Clausius Clapeyron, the pressure. Saturated vapor pressure over ice is much larger. It's smaller than over water. So all water, all liquid will go into ice. Some of the little droplets will freeze, and this will increase rapidly. But as soon as it starts increasing, they will start interacting and growing by collision and coalescence very quickly, become very big stones that are falling. They can melt and fall as rain. They can fall as hail. So basically, the only difference between these two scenarios, and as soon as you get ice, you get lightning also. It's one-to-one relationship. The only thing is how you start with large liquid droplets that fall and then the rain dissipates, or if you go on and get the ice phase going. So.
Hi, thank you for your talk. You said that during Go Amazon, 2014, 2015, we were unlucky and we couldn't see much mesoscale convective systems.
Mm-hmm.
And of course, I don't think that you think that we were unlucky, so I would like to think what's your feeling about it. And because, of course, since I'm analyzing trends, then I don't know if this has something to do. Could it be a trend? What do you think about it?
I don't know if anybody has an explanation of why. Well, there's this, you could have a more active ITCC with subsidence, whatever. The thing is that both years, there's a downfall of MCS. Of course, we were unlucky from my point of view. Somebody else might think they were lucky because they could see more widespread convection, not organized systems. So yeah, that's something that should be looked into more carefully, probably. Why?
Okay, then, thank you. Well, we have to move on.
I have one question.
Oh, we are already late, but...
Very quick. So why is the aerosol source? Is the natural source of emission, human emission?
Biomass burning, mostly.
Or biomass?
But if you go close to Manaus or Belém, the big cities, then you will have urban sources also.
So if that is biomass, then suppose you have a drought in Amazon, and this process would produce a positive feedback because the drought would make...
There are also hypotheses.
More aerosol, and then more aerosol.
And then more...
Less rain.
Well, in the transition season, as soon as you start cleaning up, it starts raining, you start cleaning up, then you go into rains that are in a cleaner environment. So this is the transition between dry and wet. During the wet season, the atmosphere is much cleaner. So the timing of the effect is basically the transition.
Okay. Thank you. Then, well, now we have a coffee break. Please be back at 11:15. I can ask a question now. I can ask. Okay, yes, please.